This video is entitled The Fundamental Postulate of Quantum Mechanics. And I think we'll have to attribute that to Schrodinger. What came before Schrodinger and why do we call it a postulate? Because it's an educated guess. An educated guess. Now, what's an example of other postulates? Isaac Newton in the 18th century. Second law is the most important one because you can derive the first and third law from the second law is force equals mass times acceleration. From classical mechanics to quantum mechanics, we need to improve on Newtonian mechanics by using this nice Italian Lagrange. Lagrange came up with Lagrangian mechanics. And another improvement on Lagrangian mechanics was Hamiltonian mechanics and the principle of least action, which is a beautiful way to describe how nature operates. Now, if these concepts are new to you, then go back and watch these 3 videos. Photons take the least action path, Lagrange video, and Hamiltonian video. All 3 of those are in a separate playlist, so look for that. Then, of course, the playlist that this video is included in, which is In Search of a Quark. In that In Search of a Quark, you'll look at de Broglie and his idea, not his idea, but his derivation of the idea of matter waves. So instead of particle behavior, we have matter being particle and wave behavior. From de Broglie actually came Schrodinger, who says that this wave property can be put in the form of a differential equation. And this differential equation becomes the primary postulate of quantum mechanics. And again, remember, it's a postulate. And as time goes on, maybe we'll find out that that postulate is not exactly true. As in the case of Newtonian mechanics, we find out that that postulate was incorrect because of the fact that matter follows wave properties. Okay, this should look very familiar, and you think, oh, well, that's obvious. It's very easy. Force equals mass times acceleration. That is Newton's second law, or let's call that Newton's postulate. Now, here's Schrodinger's postulate. H bar squared, that's Planck's constant, over 2m, that's mass. That's the same mass that's up here in Newton's thing. The second partial derivative of a function with respect to x plus potential energy, which is a function of x, times that function equals the energy value times that same function. How do we make sense of this? I think maybe you can get an idea why it takes such a big jump to go from this postulate to a postulate like this. How do we get from here to there? How do we get from here to there? Well, let's point out some things that just in its form kind of looks like kinetic energy in a way. this kind of looks like, well, this is potential energy in a way, and this is energy. So you could say kinetic energy plus potential energy equals energy. But what's this thing? What's this pitchfork thing, which is the Greek letter psi? What is this? What Schrodinger's equation here, says right here is that whatever solves, whatever function works in this scenario is the state function, or it solves that thing. When we were talking about state vectors, and for instance, we had a momentum operator, we had a position operator, and we had a Hamiltonian operator. Those are the main ones that we talk about in quantum mechanics. So let me start by solving some of this stuff with Newton. And what I'm going to do is I'm going to use momentum instead of acceleration in this. So if we put this in that form, then let me come up here and choose the little brush thing. And I'm going to say that force equals the derivative of momentum, which uses the letter P with respect to time. Now let's see if that makes sense. Well, mv, m is not going to change, but v is going to change with respect to time. So really this is m times a. It's just put in a different form. And the reason why I want to do that is in quantum mechanics, acceleration and force is not so important, and especially force is not so important, but potential energy is. Now, let's see if we can come up with an equation in classical mechanics that looks kind of similar to this. Well, let me take this form here and let's talk about potential energy. Potential energy, in other words, if you move a rock up a hill, you're giving it potential energy as far as gravity is concerned. So normally we say potential energy can be determined by, and so if I take the integral of dx and force is constant all the way through, then that's going to just be F times x. So if you're raising something above the ground and you use x as the dimension above the ground, then that's going to give you your potential energy. Now, in a similar way, I'm going to use Newton's second law to figure out what kinetic energy is. Going all the way back to the basics here and going slowly with this video. So the kinetic energy is going to be equal to the integral of, and let's see what we've got here. Well, the integral of, remember, F equals dp over dt, or the first derivative of momentum with respect to time. So I'm going to say dp over dt, and I'm going to use that same dx. So if I integrate this thing, now let's see if you can follow this so I don't have to redraw this too many times. If I take this integral and say dp dx over dt, then that looks like velocity. Let's see if you can follow this. M times v is velocity, is momentum. So how about if I just do this and put a p over m? I take momentum, m times v, and divide it by m. I've got back to v, And so then I can put dp out here. Now, if I do the integral of p and m is a constant, we'll bring that out front, then that's going to give us p raise the exponent 1 and divide by that same number, which is 2 p squared over 2m. So here's the kinetic energy, p squared over 2m. And this is going to be really important for comparing this up here. So if you followed that a little bit, then let's do potential energy as, just call that a function of x, the potential energy. And then I'll say classical, which is Newtonian stuff, is p squared over 2m plus v of x, which is potential energy as a function of position, and this equals E, total energy. So you see some similarities there between that? Now, what are the things that quantum mechanics brings into play? Well, one is that according to Einstein, E equals momentum times the speed of light. Now, you're probably thinking I was going to put E equals mc squared, but from some other stuff, this is also one of the relationships that's true. From Max Planck, his study of electromagnetic radiation, he came up with energy is equal to hf. So you notice this. You notice that this P is there. That's important. That P is similar to what we used up here. So this momentum, that's why this is important. And of course, Planck's constant gets involved. And there you notice there's Planck's constant up there. So if we look at these two, we can say that, and go back to blue or it looked kind of stupid, this PC equals HF. Okay, the speed of light. Okay, do you buy that? Taking this speed of light, the speed of light would be equal to the wavelength of a particular light wave times the frequency would give us the speed of that, and that should all be equal to the speed of light if we're just talking about light. So that should allow me to do this. And go back to blue, and that means P wavelength equals H. This is de Broglie, and then the wavelength equals H over momentum. And what's strange about that is that light does have a momentum, as well as do matter and all those kinds of things. How do we find the solution to this? Well, what does the experimentation show? That matter can act like a wave. If you have the momentum, that's mass and velocity of a particular, let's say, an electron or other piece of matter, that it does have a specific wavelength, which means it's wave nature. So let's go back to, let's see, what do we do? Well, wave functions can be something like this. Cosine 2 pi times frequency, if we do radian measure, or it could be sine 2 pi times frequency, or it can be a combination of both of these. One way that we can represent this is using imaginary numbers. Cosine 2 pi f plus I sine 2 pi f. Now, why would I want to do that? Why would I want to confuse this whole issue? Because what I want to show is that this is equal to e, base of the natural logarithm, I 2 pi f, where that's the angle. That's the radian angle of that. So here's my equation of a wave. But the wave isn't standing still, so I have to represent it a little bit differently. Oh, I guess I left off one thing. We've got to have time involved here. So I needed a t here, and I needed a t there. This will give me little places. So there we go. I put the t there. All right. Classical wave function. Now I'm going to get rid of the cosine and sine, and we'll just deal with this thing right here. If this thing is moving in space, then I've got to have a position thing that ties all this stuff together. So see if you can follow my next thing. Okay, let's see if I can bring this together now. The I, instead of 2 pi ft, we've got to put a distance thing in here that shows that over time it's actually going to be moving through space. So I'm going to put a parentheses here. I'm going to put a 2 pi over the wavelength times x minus what I had before, 2 pi frequency of the wave times t. This is all classical wave function. You don't see any momentum or anything like that in there. So what do we make of this? Let's kind of look at this and see if you've got any problems looking at it. Let me slowly go through this. Well, any place that we look at on the x-plane, this will define what that x value is. In other words, that is going to be moving up and down with the wavelength, and the 2 pi ft is going to be subtracting from that. So that'll give us the actual wave as it moves through space. So if this still doesn't make sense to you, then maybe go back and look at your classical wave functions, because we're trying to solve this deadly thing up here, this Schrodinger thing. So that's the one that we've got the most headaches with. So what if I take this value and substitute it in down here? What would that look like? And I guess I should put the quantum. Let's do quantum. Quantum version of this is E I got 2 pi. And if I plug in for 2 pi and I invert this fraction, so it's going to be P over h. That's what plugged in for the wavelength. And then x, and then minus 2 pi f t. If we want to look at this frequency thing, there's a way we can substitute in for that with the quantum mechanical stuff, and that's using the idea that E, oh, this is looking beautiful, E equals HF. So if we look at this, we can plug in for F as E over H, E over H. Now, what do I have? Notice that I can factor out a 2 pi over H and come up with this result. E to the I, 2 pi over H, well, H bar, which is what we have up here in the Schrodinger postulate, is equal to H over 2 pi. So really I've got H bar in the denominator, so it's I times 1 over H bar P x minus E t. What do you think of that? Are you mathed out? The math sometimes kind of makes your head swim. So let's use some words and maybe some ideas. Okay, we've got Newtonian stuff, and then we've got kinetic energy and potential energy, which is used all the time. Usually 1/2 mv squared, but we do it p squared over 2m because we want to focus on momentum. That's what's in the de Broglie thing. So all I'm going to do is take classical mechanics and substitute in de Broglie's thing into the classical wave equation. Now, the classical wave equation, that might not seem so obvious to you because we've got that uh, uh, E to the I, blah, 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 blah. But that's just, I'm not going to take too much time on that. I'm just going to stay with that. So, what do I do next? What comes next? Well, we're going to take that wave equation that has de Broglie's and we're going to test it with Schrodinger's postulate and see if it all plays out. We have to test to see that it's a solution. Otherwise, that nice little wave equation with P times X and E times T in it, which seems like it's going to be neat. We can use the momentum operator on it. We can use the position operator on it. And, I don't know, the Hamiltonian operator, that's a little more complicated, but we have to test that to see if that's going to work too. So if you're ready, I'm going back to the drawing board and coming up with some more stuff that way. Okay, let's see how good your memory is. What is this? What is this? This is Schrodinger's postulate, which is what this video is all about. Schrodinger's postulate, negative h bar squared. Now what's h bar? H bar is Planck's constant over 2 pi. 2m, that's mass, 2 times m, and this is the partial derivative of some function. Now, that means that we're taking the rate of change of something, but it's only with respect to x. So we're only looking at x type stuff. This is v of x, which is going to represent potential energy, or v of x is potential energy, times this function that we're going to try to test. And then this is E, energy value, and psi. Here's the function that we developed earlier. That's e to the I, which is the square root of -1. Weird, weird, weird. But this is the wave function that Schrodinger proposed as one of the general solutions. It's not all of the general solutions, but it's actually one of the easier ones, if you can believe that. So let's test to see what the second derivative, the second derivative of y with respect to x is. Well, to find that, I'm going to take the first derivative. The first derivative of this function, e, is with respect to x, is simply the same thing. That it turns out that the derivative of e to a power is that same thing, e to the power. So notice I just copied it down here. Now, what's all this garbage out here? Well, in addition, because it's with respect to x, we have to take all of this exponent with respect to x. Px is a constant as far as x is concerned, and this whole quantity has no x in it. So it is going to be 0. That's why I've got the 0 out here. So notice this is I over h bar px. That's the first derivative. Now, what's the second derivative? Well, just to make things easy, I restated the first derivative, I over h bar px psi, which is this state function that we're testing. Remember, it's this function up here. And then the second derivative is the derivative of that first derivative. Here's the first derivative. Derivative of a derivative is the second derivative. So I've got IH bar PX from the first one. And then when I took this again, it's IH bar px again times that function. So I just replaced this whole thing with the same thing down here. And if you multiply these two together, square root of -1 squared is equal to -1 px squared and h bar squared psi. Okay, if you're ready, even if you aren't, I'm going to push ahead here. Here's the second derivative of psi with respect to x, and I'm going to plug it in over here into this deal right there. Okay, let's go back to blue and plug it in. That's negative h bar squared over 2m times, plugging that in, it's going to be negative p momentum in the x dimension squared over negative h bar squared times the function psi. And what does that leave me? Well, that comes up with, let me go ahead and carry this other stuff out just in case we get lost, which is quite possible. Let's multiply these two things out. And I get to do the red marker because I'm going to cancel stuff out. So these things go away. And lo and behold, I come up with these two things cancel, and the negatives cancel as well. So let's see what I come up with is, hey, this is kind of neat. P sub x squared over 2m. Now, if you've been listening, you know what this thing is right here. This is kinetic energy times the psi function plus v sub x times the psi function equals the energy value times the psi function. Now that E is total energy. So what if I brought this thing over here and said the kinetic energy, P sub x squared over 2m equals, well, I have to put the psi function there, equals E to the psi function minus v sub x times the psi function. And then what can I do? Get out my little red thing to emphasize something. There's a psi function, psi function, psi function. What if I divide both sides by the psi function? Then you get kinetic energy equals total energy minus potential energy. So it works. It really works. So Schrodinger's postulate is proven. At least as far as I'm concerned, it's proven. Did you get anything out of this? This is the big deal about quantum mechanics is Schrodinger's postulate. Now, Schrodinger's postulate only applies to the time independent stuff. The time independent stuff. You notice we didn't pull energy out of this. We can pull momentum out of it, we can pull position out of it, but it only does the time independent stuff. You notice in that function there was an energy T that if we could take the derivative of that thing, then we could pull out the, with respect to time, then we could pull out the energy. So we need the time dependent part of this whole thing. And guess what? That's going to be another video.